Welcome back to the Deep Dive. Today, we are not just scratching the surface. We are essentially drilling down into the bedrock of modern AI.
We really are.
Yeah, we're looking at a document that, in retrospect, it feels like a historical turning point. Usually in tech, we talk about iterative updates.
Right, like faster phones or slightly better screens.
Exactly. A little more battery life. But today, we're talking about a moment where the line on the graph didn't just go up, it went vertical.
It really did. We are analyzing the paper PaLM's Scaling Language Modeling with Pathways. You can find it on ARC5. It's 2204.02311. And honestly, the scale of what we're covering today is just, it's mind-bending.
Mind-bending is definitely the right word. We're talking about the PaLM model. But before we even get into what it does, I want to talk about the sheer mass of this thing.
The 540 billion parameters.
Well, 540 billion. I feel like we throw around the word billion a lot in tech, like it's nothing. But for you listening, we really need to contextualize that. What does 540 billion parameters actually look like in terms of a machine?
Well, it's an enormous number of tunable weights. Think of parameters as the connections between neurons in a brain. They're the knobs and dials, the model twists to understand the world. To give you a comparison, GPT-3, which was the titan of the industry before this, had 175 billion parameters.
Wow.
Yeah, so PaLM is more than 3 times that size.
So it's not just a little bigger. It's a completely different weight class entirely.
Completely. And looking at the author list gives you a sense of the effort involved here. It's led by Akanksha Chowdhury, but there are 66 other authors listed.
I saw that. 66 authors. That's not a research team. That's a small village.
It is. And it includes heavy hitters like Jeff Dean, too. This signals that this wasn't just a side project or a simple academic experiment. This was Google throwing the weight of its entire research infrastructure at a single fundamental question.
And that question seems to be, what happens if we just go bigger?
Exactly. And here's the nuance. It's not just bigger is better. The mission here was to test the limits of scale using a very specific new architecture.
The pathway system.
Right? Pathways. They weren't just trying to build a chatbot. They were trying to prove that if you scale a model enough, using the right system, it doesn't just get better at the things it already knows. It actually starts doing things it was never taught to do.
That's the spooky part we'll get to later, the discontinuous improvements. That's the real hook of this deep dive. But we have to eat our vegetables first.
We do.
We have to understand the engineering. Because you can't just buy a hard drive, download 540 billion parameters, and hit run, right?
Oh, definitely not. The logistics alone are a nightmare. You're talking about a dense transformer model so large it cannot fit on a single chip, or even a single server rack.
So let's break down the pathways part of the title. What exactly is Pathways? Is it just a fancy name for their server room?
Not quite. Think of Pathways as the conductor of a massive, chaotic orchestra. To train PaLM, they used 6,144 TPU v4 chips.
6,000 chips?
Yeah.
I'm just imagining the electricity bill for that. That's a lot of heat.
It's an immense amount of compute. Now, here's the problem. Traditionally, when you train a model across that many chips, you run into a bottleneck.
How so?
Well, you have to split the data up, send it to different chips, have them do the math, and then sync everything back up. That synchronization is usually where things slow down.
I see.
It's like trying to get 6,000 people to agree on a dinner order before anyone is allowed to take a bite.
Right, so you have efficiency loss. You spend more time coordinating the chips than actually learning from the data.
Exactly. This is known as the pipeline bubble problem. Pathways is a machine learning system designed to handle that orchestration asynchronously and efficiently across multiple TPU pods.
So it groups them.
Right. It basically treats the entire data center as a single computer. It allows the model to be sharded or split up in a way that keeps those 6,000 chips busy almost 100% of the time.
So Pathways is the infrastructure layer that makes the 540 billion parameter size even possible in the first place.
Exactly.
Without Pathways, the training would take, what, decades?
Or it would just be remarkably inefficient and completely cost prohibitive. The paper emphasizes that this isn't just about the model architecture, it's about the system architecture.
Yeah.
They achieved a training efficiency of 57.8% hardware FLOP's utilization.
I know 57% sounds like a failing grade in high school math, but in supercomputing, that's actually incredibly high, isn't it?
It's phenomenal. Usually at this scale, you lose so much to overhead like data transfer, waiting for other chips, that you're thrilled with 30% or 40%.
Wow.
So getting nearly 60% utilization on 6,000 chips is an engineering marvel in itself. It means they are extracting almost every ounce of performance those chips have to offer.
Okay, so they have the engine pathways, they have the fuel, massive data sets,
Right.
and they built this 540 billion parameter dense transformer model. Let's pause on the word dense for a second. We hear about sparse models sometimes, where only parts of the brain turn on. Why do they go dense here?
A dense model means that for every single token, every word or piece of a word the model processes, all 540 billion parameters are active. Every single neuron fires.
That sounds incredibly expensive. Why do that instead of the sparse approach, which saves energy?
The hypothesis was that dense models generalize better. If you have a sparse model, you're essentially routing tasks to specialized subnetworks. With PaLM, the whole brain is engaged for everything.
I get it.
The idea is that this creates richer representations and deeper connections between unrelated concepts. It's brute force, yes, but it's brute force aimed at creating a unified understanding.
Which brings us to the actual performance. The abstract throws around this term, few-shot learning. Now, in the old days, and by old days I mean like 3 years ago, if I wanted a model to translate English to Swahili, I'd have to fine-tune it.
Right.
I'd feed it a data set of thousands of English-Swahili pairs and completely retrain the weights.
Exactly. You were essentially teaching a specialist. You'd take a base model and turn it into a dedicated translation bot.
But PaLM is different.
Very different. PaLM is a generalist. Few-shot learning means you don't retrain the model at all. You just give it the prompt.
Just the prompt.
Yep. You say, here's an English sentence, here's the Swahili translation, here is another pair, now translate this third one. You give it a few shots, a few examples in the prompt itself.
And it just figures out the pattern on the fly.
Yes. And what this paper showed is that as you scale the model up, that ability to learn from just one or two examples doesn't just improve linearly, it skyrockets.
That's incredible.
PaLM achieves state-of-the-art results on hundreds of language understanding and generation benchmarks using just this few-shot method, often beating models that were specifically fine-tuned for those exact tasks.
That is the death knell for the specialized model era, isn't it?
Mm.
Why build a specialized medical bot if the giant generalist bot is smarter than your specialist after reading just 3 medical charts?
That's the big question the industry is wrestling with right now. It suggests that general intelligence, when scaled up, subsumes specialized intelligence. But the most important part of this paper, the part that really shook the researchers, was the way that performance improved.
The discontinuous improvements. I love this phrase.
It's the core finding of the whole paper.
Let's drill into this for everyone listening, because intuitively we think of progress as a slope. If I have a 100 billion parameter model, it's smart. If I have a 200 billion, it's smarter. 540 billion, it's smartest. A nice smooth line up and to the right.
And for many simple tasks, that actually is true. If you look at something like basic grammar correction, the curve is relatively smooth, but they tested PaLM on a suite called Big Bench.
Big Bench. Subtle naming convention there.
It fits perfectly, though. It's a massive benchmark collection of difficult, diverse tasks, logic puzzles, identifying metaphors, obscure reasoning problems, understanding humor. And on a significant number of these tasks, the performance curve wasn't a line, it was a step.
A step, like stairs.
Exactly. Imagine you test the 8 billion parameter version of the model on a specific logic puzzle. Performance is near zero. It's essentially guessing randomly.
Okay, so it's clueless.
Then you test the 62 billion parameter version, which is a huge model in its own right. Performance is still near zero. It hasn't learned a thing.
So you've added over 50 billion parameters, spent millions on training, and gotten absolutely nothing. That's depressing.
It really looks that way. But then you test the 540 billion parameter PaLM. Suddenly, performance steeply increases. It jumps to 80% accuracy.
It goes from 0 to hero instantly.
Instantly. It's like the model was staring at the wall for the first 2 stages, and then suddenly the lights turned on. It finally got the concept. This is what they call discontinuous improvement.
That is wild. It implies that certain capabilities are locked behind a complexity gate. You need a certain amount of neural mass before the concept even registers. And, I mean, they even mentioned it outperforms average human performance on the big benchmark, right?
It does, and this changes how we think about risk and development. Because if you are testing a smaller model and it can't do a specific task, you might assume, oh, AI just can't do this. But you might just be one scaling step away from it suddenly being able to do it perfectly.
It's like water boiling. You heat it up, it's water. You heat it more, it's salt water. Then you hit 100 degrees and boom, it's steam. Totally different state.
That is the perfect analogy. It's a phase transition. The capabilities aren't being built brick by brick. They are emerging from the sheer complexity.
So what kind of tasks showed this pop? Was it just obscure trivia?
No, it was reasoning, specifically multi-step reasoning. This is one of the biggest wins for PaLM. They used something called chain of thought prompting to really leverage this.
Chain of thought. Is that where you tell the model to show its work?
Pretty much.
Yeah.
Instead of just asking for the answer, you give the model an example where the reasoning is written out step by step. Let's take a math word problem. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 balls. How many does he have now?
Okay. If I just ask a small model for the answer, what happens?
It might just guess 10 or 8 because it sees numbers in the text and tries to smash them together. It doesn't actually understand the sequence of events.
But with chain of thought.
With chain of thought, the model learns to output. Roger started with 5. 2 cans times 3 balls is 6. 5 plus 6 is 11. The answer is 11. PaLM, specifically the 540 billion version, became incredibly good at this.
It learned to think before it spoke. It's simulating a thought process.
It learned to decompose complex problems into intermediate steps. And here is the kicker. On a specific benchmark of math word problems, PaLM with chain of thought prompting actually outperformed the fine-tuned GPT-3 state-of-the-art.
Again, the generalist beating the specialist, but beating it at math. Large language models are notorious for being bad at math. We usually say they are word calculators, not number calculators.
That's exactly why this was such a big deal. It showed that reasoning might just be a downstream effect of language proficiency. If you understand language deeply enough, if you understand the relationship between words like each, more, and total, you start to understand the logic encoded in the language itself.
That's a profound thought. Logic is just syntax with consequences.
Yeah.
If you master the syntax perfectly, you get the logic for free.
That really seems to be what is happening at 540 billion parameters.
So it can do math word problems? What about the other language of logic? Code. Because I know a lot of engineers are looking at this nervously.
Huge improvements there, too. The paper shows strong capabilities in source code generation. And this wasn't just copying snippets, it was solving actual coding challenges. They demonstrated this across a wide array of benchmarks. Generating Python code, translating code from one language to another, and even fixing bugs.
And again, this was the exact same model. They didn't swap in a coding module or plug in a distinct math brain.
Same model, same weights, just a different prompt. It can switch from writing a poem about a sunrise to debugging Python code without missing a beat. It also showed massive gains in multilingual tasks, even for languages that made up a tiny percentage of its training data.
That's the transfer learning magic, isn't it? Learning the structure of English helps it understand the structure of Swahili, even if it hasn't seen much Swahili.
Exactly. Concepts are universal. A cat is a cat in every language. Once the model understands the concept of a cat in the dense vector space, the label, whether it's cat, gato, or neko, is just a surface detail. The 540 billion parameters allow it to map those concepts universally.
Okay, so we have established that this thing is an absolute beast. It's smart, it reasons, it codes, but I want to play devil's advocate for a second.
Go for it.
Is it actually learning, or is it just memorizing? Because with 540 billion parameters, that's a lot of storage space.
Yeah.
Could it just be storing the entire internet and looking up the answers?
That is a critical question, and the authors actually address this specifically in the paper's analysis section. They ran a study on training data memorization. They wanted to see if the model was just regurgitating training data, like repeating specific sentences or strings of text it had seen before.
Right, the stochastic parrot argument. Is it thinking, or is it just repeating what it was told?
They found that as you scale up, the capacity for memorization does indeed increase. A bigger brain has more room to store exact snippets. If you feed it the first half of a unique sentence from the training data, the 540 billion model is more likely to finish it exactly than a smaller model.
So there is some memorization happening.
There is, but, and this is the key but, the performance on reasoning tasks, specifically on novel logic puzzles or unique math problems that do not exist in the training data, proves that it's not just memorization. You can't memorize the answer to a math problem that has never been written down before.
You have to actually solve it.
Exactly. So while memorization is a factor and a technical challenge they have to manage, The reasoning capabilities are genuine emergent behaviors. It is synthesizing information, not just retrieving it. And the paper doesn't just stop at memorization, they also heavily audit the model for bias and toxicity.
Which is crucial when you're absorbing that much of the internet.
Right. The authors discuss the ethical considerations related to large language models and propose potential mitigation strategies. They're looking at the bigger picture and the risks, not just celebrating the benchmarks.
That distinction is everything. Retrieval is a search engine, synthesis is intelligence. And then managing the risks of that intelligence is the next massive hurdle.
Precisely. And PaLM seems to be crossing that synthesis bridge.
So let's zoom out for a minute. We have PaLM, 540 billion parameters. It's organized by this pathway system that turns a data center into a single brain. It's showing these sudden, discontinuous jumps in capability. What is the takeaway for someone listening to this who isn't a machine learning engineer? Why does this paper matter to them?
The takeaway is that we are in a new era of big science for AI. The barrier to entry for creating these foundational models has become astronomical. You need 6,000 TPUs, you need the pathways infrastructure, you need millions of dollars in electricity.
So the power to build these things is concentrating. You can't build PaLM in your garage.
No, you can't. The power to build is concentrating, but the power to use is democratizing. Because PaLM shows that a single model can handle hundreds of tasks. It means that downstream, users might just need one API to do everything. Translation, coding, creative writing, analysis. You don't need to be an AI expert to use state-of-the-art AI anymore. You just need to know how to prompt the generalist.
It simplifies the application layer while complicating the infrastructure layer. We are moving toward a utility model. You plug into the grid, the PaLM grid, and you get intelligence.
Exactly. And the second takeaway, and this is the one that really keeps me up at night, is that we don't know where the ceiling is.
That goes back to the discontinuous improvements.
Right. If we saw these spikes at 540 billion parameters, what happens at 1 trillion? What happens at 10 trillion?
We saw reasoning pop into existence at 540. What pops up next? Is it long-term planning? Is it genuine creativity? Is it the ability to invent new physics?
We honestly don't know. The paper proves that capabilities can remain entirely dormant, sitting at zero until you hit a critical mass. We might be sitting on zero capability for something incredible right now, just waiting for the next order of magnitude and scale.
That is both the most exciting and the most unnerving thing I've heard all week. It means we are exploring a map where the terrain reveals itself only as we step on it. We don't see the mountain until we bump into it.
That's the reality of large language models right now. We are building them to find out what they can do, not the other way around. PaLM is a massive signal that the bigger is better hypothesis has a lot of runway left.
Well, on that note of exploration and the great unknown, I think we'll wrap up this deep dive. We've covered the hardware, the architecture, and those sudden stair-step spikes in intelligence that PaLM introduced to the world.
It's a dense paper, but a truly foundational one. It really set the stage for everything that is happening now.
Absolutely. So for you listening, keep an eye on those parameter counts. They aren't just vanity metrics. They might be the countdown to the next big aha moment where a computer suddenly learns to do something we thought was impossible. If performance drastically spiked at 540 billion parameters to outperform humans on Big Bench, what kind of discontinuous improvements might we see at the next level of scale? Are there other capabilities waiting to suddenly turn on? Something for you to mull over. Thanks for listening, and we'll catch you on the next deep dive.
Stay curious.